Welcome to this explainer on the Database Management System course, CSPCC304 for short. Look, we're not just memorizing dry theory today. We're literally learning how to build the back end of the modern digital world. Think about it. Every single app you use, every online purchase you make, every digital record out there, it all relies on the exact concepts we're going to unpack right now. Okay, let's dive into this. Here's our roadmap for transforming raw data into a fully functioning application. We'll start with an introduction to database systems, move on to modeling the real world, and then master SQL commands. After that, we'll tackle normalizing relational schemas, managing concurrent transactions, and wrap it all up with course logistics and assessments. Let's kick things off with Module 1, Introduction to Database Systems. I want you to imagine the absolute sheer chaos of unstructured information. Picture millions of patient records, bank transactions, or student grades just floating around in random, messy text files. A standard file system is exactly like that. It often leads to super redundant data. You might update an address in one file, right? But then completely forget to update it in another. A database system, on the other hand, is a game changer. It takes that raw, messy data and turns it into highly usable, reliable information, guaranteeing data integrity, robust security, and the massive scalability we actually need for modern applications. Now, this brings us to an absolutely crucial concept: physical data independence. This is a foundational pillar of database architecture. Basically, it means that if we change how data is physically stored on the hardware, like, say, upgrading a massive hard drive or switching up a storage format, it will not break our logical application programs. Our apps don't need to know the complex physical mechanics under the hood at all. They just need access to the data. It's exactly what keeps our system so remarkably flexible. Moving right along to Modules 2 and 3, Modeling the Real World. You know, before you lay even a single brick for a new building, you have to draw the architectural blueprints. Well, designing a database is exactly the same thing. To do that, we use the essential building blocks of the Entity Relationship, or ER model, and the Extended ER model. We start with entity types. These are basically the things in our database, like patients or doctors. Then we have attributes, which describe those things. Keys are used to uniquely identify these entities. And relationship sets? They define exactly how these entities interact with one another. Oh, and we even have weak entities for data that entirely depends on something else to even exist. To really ground this theory and put it into perspective, the syllabus focuses on a real-world case study, like designing a robust backend for a hospital management system. We take all those abstract entities and relationships we just talked about and use them to accurately map out real things: doctors, patients, hospital wards, medical treatments. The ultimate goal here is to take this conceptual ER model and convert it into a strict, perfectly functioning relational schema. Next up is Module 4, Mastering SQL Commands. Okay, so you've drawn the blueprint. Now you have to actually build the structure. SQL is the language we absolutely must master to speak to and command our database. And this brilliantly illustrates how we manage everything, broken down into 3 specific buckets. First up, Data Definition Language, or DDL, which we use to create and modify the database structure itself. Second is Data Manipulation Language, or DML, and that's for querying, inserting, and updating the actual data. And third, we have Data Control Language, DCL, which handles all of our system security. Speaking of security, let's take a closer look at these data control commands, grant and revoke. I love to think of these as the digital bouncers of your database, because let's face it, in a multi-user environment, you definitely do not want everyone having access to everything. These commands strictly enforce security and multi-user authorization. They allow you to grant specific access permissions to a user, and then revoke them just as quickly to keep your data completely safe. Now we arrive at Module 5, Normalizing Relational Schemas. Think of normalization as your ultimate organizational tool for cleaning up messy, redundant data. It's a very systematic step-by-step process where we apply specific design guidelines based on what we call functional dependencies. We start at the first normal form to ensure atomic values, and then smoothly progress through the second and third normal forms. Eventually, we reach the advanced Boyce-Codd normal form, or BCNF. With every single step, we systematically eliminate data anomalies, wipe out redundancy, and drastically improve the overall efficiency and integrity of our database design. Which brings us to Module 6, Managing Concurrent Transactions. I like to think of this particular section as traffic control. We have to ask a really critical question here. When thousands of users are querying and updating data simultaneously, how on earth does a database handle it all without just crashing? Imagine a scenario in our hospital management system where two different receptionists accidentally assign two totally different patients to the exact same hospital bed at the exact same second. No way, right? It would be absolute, utter chaos. So, the answer to preventing that chaos lies in the ACID properties. These are the unbreakable rules of transaction management: atomicity, consistency, isolation, and durability. They guarantee that even if there's a huge system failure or just a bunch of multi-user executions happening at once, our transactions remain perfectly safe and data consistency is strictly maintained. Basically, it works like this: a transaction either fully completes or it completely rolls back as if it never even happened at all. To actively enforce those unbreakable rules, we use concurrency control. The syllabus specifically highlights lock-based and timestamped-based protocols. You can think of these as the intelligent traffic lights of our system. They expertly manage who gets access to what data and when, actively preventing the whole system from freezing up in what we call a deadlock. And hey, if a failure does somehow occur, log-based recovery acts as our ultimate safety net to restore the system. And finally, we've reached the finish line: course logistics and assessments. Let's outline exactly how success and progress are measured in this highly practical 3-credit course. The grading mechanics for the semester are actually crystal clear. Out of 100 total marks, 20 are dedicated to continuous assessment. Then, 30 marks go to the mid-semester exam, which covers roughly the first 40 to 50% of the syllabus. And finally, the big one: the last 50 marks are decided by the comprehensive end semester exam. Let's zoom in on that continuous assessment slice for a second. Half of those 20 marks, so 10 marks, are specifically for a live problem or case study. And this isn't just a basic written test. You are required to research, collect resources, create a back-end for a real-life problem statement, and then deliver a 10 to 15-minute presentation on your database design. The remaining 10 marks? They're split evenly: 5 for a think-pair-share activity and 5 for your general regularity and class participation. We're going to wrap up this explainer with a pretty profound thought taken directly from the program outcomes listed in the syllabus. Identify historic points of technological advance to stay current regarding new developments in your field. This ties perfectly into the concept of lifelong learning. You see, this course isn't just about passing an exam. It's about truly grasping the foundations of how our technology works. So I'll leave you with this final question to think about. Once you've completely mastered these fundamentals of database systems, how will you continue to keep your skills sharp in our ever-evolving digital landscape?